Hello, it's Keith here, and this is lesson 3 of my ARM assembly programming tutorials. Now, last week's lesson on the addressing modes was a little bit tough. We went through a lot of content and it was maybe a little bit stressful, but this week's going to be a lot easier. This week we'll be looking at the condition codes, the flags, and how we can perform commands like jumps based on the different states of the flags, which of course set by our other commands. We'll be going through a lot of examples, seeing all of the condition codes and how they work, and we'll learn basically how things are operating on the ARM processor. Now, the ARM processor has the same kind of jump on conditions as most other processors do, but the ARM has something fairly special that most of them don't, and this is the ability to conditionally execute a large number of the commands the processor supports based on the state of the flags. So on most processors, if we wanted to add as value if the 0 flag was set, we'd need to jump over it if the 0 flag wasn't set. On the ARM, we can make that command only occur if the flag is set, and it's not just the 0 flag. We can do this on any of the condition codes. So it makes the ARM much more powerful because we need less branching around, and not only does this save us some code, it actually helps the optimization within the processor because the execution is more linear and there's not as much jumping around within the code because there's less branching needed, because we can do a few of our simple commands just based on the conditions. So what we're going to do today is we're going to have a look at some source code. We're going to run a lot of examples. We'll see the flags on screen. We'll see how the flags change depending on the values we're working with and what condition codes to use with those values. The intention is with this is that you download the example code we're going to be seeing today and you try things out yourself. It's not really intended you would just watch this video. You're going to need to try it out in some capacity of your own, either in your own program or using my example code. But we're going to go through as well as I can in this video, and we'll see all of the condition codes and learn what they do. Okay, so let's go over to today's source code and let's see what we're going to be working with. So here it is. We've got a bunch of branches at the top, and these will allow us to test the various condition codes and see the results. So first of all, let's execute this first one, flags test, and this will just show us the basics of the flags, and we'll see on screen the state of the flags, and we'll learn how the ARM works with flags because it is a little bit different compared to the other processors these tutorials have covered. Okay, so we're going to be using RISC-OS today, and what we're going to be showing is we're going to be showing the flags as a set of letters here. A minus means it's not set, a Z is the 0 flag, a C is the carry flag, and so on. So if there's a minus, those flags aren't set. We're going to show registers 0 and registers 1, and we're going to be using those two registers for all of our testing today. So that's what we'll be using, and hopefully this will allow us to see how things work. Now, the code that creates these is the code that's provided in this tutorial. It's too complex for today, so we're not going to cover how the code is showing these to the screen. The purpose of today's tutorial is just to learn why what was shown to the screen was shown. Okay, so what does this first test do? Well, the first test is showing something quite important about the way the flags work on the ARM, and something that's different compared to the other processors covered in these tutorials so far. Now, on most processors, a mathematical command will set the flags. On the ARM, of course, mathematical commands can set the flags, but they don't have to. So we can decide which commands alter the flags and which commands don't. Now, a add command like this will not set the flags. An add command with an S on the end, adds, will set the flags. And so by adding an S to the end of our commands, we're telling the processor to set the flags. You can see here a compare command. Now, a compare command that didn't set the flags wouldn't do anything. So we put the S at the end there. And we can do this with a large number of our commands. We could use a moves command if we wanted to set the flags based on a move. I'll just do that here. And you can see now that this N flag has been set. That's the negative flag. We'll discuss that later. But as I say, really we can set all of these commands that are able to alter the flags to do so by adding an S to the end. And if we take the S off, we won't be altering the flags. And the benefit of this, of course, is that we can selectively set the flags. So whereas on other systems we need to back up the flags at an early point and then restore them later on if our middle commands might affect them. In the ARM, we don't need to back the flags up in a lot of cases. We can just set the later commands to leave the flags alone and then do our comparison on those flags later on when we want to do so. So that's the first important thing to understand about the flags on the ARM, is that we can choose when we want to set them and when we want to leave them untouched. So you can see here that we've done a few little tests. Let's just go over the code and see what it actually did. Okay, so our first command here was loading 1 into R1 here. You can see that 1 just there. and we've loaded a test value into R0 here. Now you can see the carry is currently clear. And we've done that by just adding the R1 to R1 and storing the result in R0 here. Now we never actually saw this on screen, but of course this will not cause any kind of carry, and it's a non-zero value, so it's effectively cleared out all these flags here. And then we've loaded our true test value here into R0, and then what we've done is we have added 1 to it. We've done that just here. Now if we add 1 to a value that's filling all of the bits here, that's going to overflow the register, and that would cause a carry normally. Now in the case here though, we didn't set the S here, so even though the register is now 0 and a carry should have occurred, the processor flags haven't changed to reflect that because we didn't put that S in. Now the second time we've done the exact same thing, loaded R0 with the same value here with all the bits set to 1, added 1 to it, but this time we've put that S in to set the flags. And so you can see that the second time it rolled over, we get a 0 flag because we've now got a 0 value, and we've got a carry flag because 1 bit was pushed out of the limits of this register here. So you can see that we can do that on the ARM. We can either set the flags or leave the flags alone, and it just depends on that S at the end of the command. So you need to make sure that you're using that when you expect the flags to change, because of course that is something that's quite different to a system like the 68000. So that's the first thing we just wanted to look at there, how we actually set the flags when we want them. Okay, well, let's try another test. Let's try a test of the carry. Now the carry is used for a couple of purposes. The first is that when a register has exceeded its limit and a bit was pushed out, that bit will be pushed into the carry. Some rotation commands, the ROX, will push a bit into the carry, and also it is used in comparison operations. The flag is, although we've got special commands to actually work with that in a lot of cases. So today we're going to have a look at this. We've got basically the same example we just saw. We're loading a value here with 8 Fs, which is effectively setting all of the bits to 1. And so if we add 1 to that, there's going to be nowhere for that extra bit to go. You know, everything's already full. And so 1 bit will be pushed out. So as we saw before, if we just run this here, where you can see here that if we add 1 in the 1 in R1 here to the full bits in R0, we cause a 0 and we have a carry flag here. Now what we've got here is a couple of branch commands, branch if carry set and branch if carry clear. We've got all of these little jumps here which will just show some characters to the screen. Again, we're not going to go into how they work. The point is that we're just jumping to a routine that will show something visual on the screen to see what actually happened. So we've got this B command, which is our branch command. We can see it just here, but this time we've added 2 letters to the end of that command, CS, which is carry set. So if the carry is set, if the carry flag is true, is 1 here, you can see it is, then we will jump to the carry, and if it's not, we will jump to no carry. And if neither command occurred, which in this case is impossible, but just for completeness, we're jumping to no jump just here. So okay, so in that case the carry flag was set, we can see it just there. Well, what happens if we used a different value for R0? If we have all 1s with all of the nibbles as F, then the adding 1 will cause the carry. But if we set the last bit to 0 here and we run again, well, this time when we added 1, we actually had some space and there was nothing pushed out of the register here. So the carry is not set, the C is not set. There's an N here, that's something else, we'll get to that in a moment. But we've jumped and we've shown no carry here, NC. So the second jump occurred there. Now I can prove that to you, because if I just rem this line out here, well, now we're just shown a full stop, which is what the no jump generic ending is doing here. So you can see here that depending on whether the carry flag was set or not, we can branch if carry set or branch if carry clear. Now these also can be used for greater than and less than statements, and we'll see those in just a moment. Okay, so that's the carry being used for overflowing of arithmetic. We'll see the carry again later on, but let's now move on to testing for things being 0 or being equals also. Some of these flags have multiple purposes, and that's because of the way comparison works in processors. Now, as I say, we were using the carry there for data being pushed out, but it's also used for comparison, and in the same way, the 0 flag, which is when a register contains a 0, is used in comparisons, and that's something that's quite important. Now what we're going to do in this example, we're going to load a value 10 here, and we're going to compare R0 to R1, and in this first case both are set to 10. So when we compare them, the difference is going to be 0, and that will set the Z flag. So even though neither register is 0, the difference is 0, so the flag is set. Now the reason for this is that a compare command is a kind of fake subtraction. What it does is it performs, in theory, the subtraction of the two registers and then sets the flags accordingly, but it never alters the registers, and that's true on all processors, that's not just the ARM. So what we're doing here is we're setting the flags as if we'd done a subtraction of R1 from R0 here. And so let's see the result of that. Well, in this case, we've compared A to A, which is 10 in hexadecimal. The 0 flag Z was set, and we've jumped and shown an equals sign because we've got a branch if equals BEQ, and we're jumping to a jump equals routine that shows an equal sign. BNE is branch if not equals, and that would branch if the two were different. Now we can just of course test that as well if we just run this line out here. As I say, this is why I'm kind of recommending you download this and try these out yourself, because it will help you out if you're struggling with a few of these. But you can see here we've shown an exclamation mark equals, which is the C structure for a not equals statement. Less than greater than would be the basic version, but I thought I'd use exclamation mark here. So anyway, that's what we show if the two don't match. And as I say, this is effectively because the 0 flag is set. Now, as I say, we could equally, instead of doing a compare, we could do a sub with an S because we need to show the result, and we could do subs R0 and R1 here. And if we run this, well, you can see the 0 flag has still been set and the equals has been shown is the same as the compare command would have done. The only difference is that R0 has been changed. As I say, it's effectively simulating a subtraction when we do a compare. Now the compare command is actually a bit of a special case, because even if we don't put the S on the end, the flags are set accordingly, and that's because the compare command actually has no purpose other than to set the flags. So, but it's implied by default. But for completeness, I'm putting the S's on the end just because I want to make sure that we're clear when the flags are being set, and you need to get used to adding that S to the other commands when you're expecting your flags to be set. So I think it's nice discipline to do that. As I say, in this case, the 0 flag is being used if the difference is 0, and when we want to jump if 0 flag is set, we use branch if equals BEQ, and if we want to jump if the 0 flag is not set, we use branch if not equals, and that's how we can do the branches depending on the 0 flag on the ARM processor. Okay, well, that's how we can compare two values and see if they're the same or different. But of course, we're going to need to do things comparing a 10 and a 20 and things like that, and as a 5 and a -1. And we're going to have to work out ways of seeing if things are greater or less than, because we're going to need to check if our player's going over boundaries, if the enemy's on the left or the right of the player, and things like that. So we're going to need a way of doing that. And like on the ARM, like all processors as far as I'm aware, we have to use different commands if we're working with signed numbers that could be positive or negative, or unsigned numbers that are always positive. And the reason for this is a little bit technical. I do have some tutorials on hexadecimal numbers, positives and negatives, on my channel already, so please have a look and watch those if you're unclear on it. What we do to convert a positive number to a negative number in assembly is we effectively flip all of the bits and we add 1 to the number, and the reason for that is that when we overflow a number in a register, the number will go back to 0 and then carry on. And so a negative number like -1 is effectively all of the bits being set, because if we add that number to a positive number, the result will go down, and it will go down by 1. So as I say, I know it sounds crazy and it's a bit weird, but unfortunately that's the way it works. We'll see a little bit more of that in a moment. But the first thing to understand at this stage is we have to treat a register that we are considering to be a signed number or an unsigned number differently when we do our comparisons. In most cases they're the same. You know, we can do our additions and subtractions the same, but when it comes to comparisons, we need to tell the processor this is actually a signed number and this is an unsigned number, because an extremely high unsigned number and a slightly low signed number are actually the same value in the register. It's the commands that make the difference. I know that's confusing, I apologize, but that's the nature of the beast, so to speak, in this case. So what we're going to do here is we're going to compare a value in R0 and a value in R1 again, and we're going to do some branches based on the state of those, and we have 4 possible options, and these will use a combination of multiple flags. So when we do a comparison, we're effectively doing a subtraction, and this might cause a carry, it might also cause a 0, and so we're going to be branching depending on the 0 flag and the carry flag. Now we have 4 commands: branch if carry set, which effectively branches if the value in R0 is greater or equals than R1, and then we have branch if carry clear, and this will branch if the value in R0 is less than R1. We then have some special ones: branch if higher, and this will branch if R0 is greater than R1, and branch if less than or same, which will branch if R0 is less than or equal to R1. So we have this 4 for working with unsigned numbers. They're a little bit confusing, but I think it's going to be easiest if we actually just try them out. So let's just execute this here, and let's see what happens. So our value in R0 is 10, and our value in R1 is 5. You can see that just here. The A is of course 10 in hexadecimal, and you can see the C flag has been set. Now in this case, R0 is greater than R1, so we've branched to the greater symbol here because we've branched if it's higher. Now this one will do less than or same, so we can try this out if we want. So if we just change this to 4, well, R0 is now lower, so we have indeed branched. This branch if less than or same has indeed occurred, and we've shown the less than symbol. But of course, if R0 is 5, then this has also caused branched if less than or same here, so we've also shown the less than symbol. So these are some of the options for us down here. Of course, we also have these ones up here. Now, when we've executed here, the 2 values are the same. The carry flag has been set, so branch if carry set has occurred, and this has branched because R0 is greater than or equals to R1 here. Now, if we change R0 to a 4 here, well, this time the carry is clear, so we've branched to this less than routine here. Now, as I say, I know these were a bit of a pain because you don't really want to have to think of carries when you're doing comparisons. One advantage of the ARM is you can actually work in signed numbers all of the time if you want, because our registers are so huge and these systems have a lot more power. In 8 bits, if you're working with 8-bit registers, you can't treat all of your numbers as signed because you would be limited to plus 127 or to minus 128. But with 32-bit, you could do, so it's entirely up to you. But as I say, if you're wanting to work with unsigned numbers and do these less than greater than comparisons, unfortunately, you do have to use the right commands accordingly, depending on whether you want greater than equals, less than, or greater. Of course, you can also do the comparison to equals in a separate stage with the BEQ statement, but these commands will do the 2 together. Okay, so those are how we can compare unsigned numbers here, which of course is just positive numbers with no comparisons to negatives. We do, of course, have the signed version, and the code here, let's have a look at it. And here it is. So this time we are able to work with signed numbers. Now you can see the first one is actually unsigned. We have some commands here: branch if greater than, branch if less than, branch if greater than equals, or branch if less than equals. And we're showing the greater than or less than symbol once again. So let's just try the first example with our positive numbers here. Okay, so R0 is 10, R1 is 20. So we have branched if less than because R0 is less than R1, and you can see that has worked just fine. Okay, well, let's try a negative value. Let's try doing minus 30 here. Well, R0 is still less than R1, so we've shown a less than here. But you can see here that this value is very strange indeed. Now this, if you think about it, this is kind of like a very large number, but it's actually a slightly small number, and this is why we need to use the right commands when we're dealing with negative or positive numbers. Now, as I say, the thing is with negative numbers is if we set this to just -1, well, you can see here that that has set FFFF here. And the reason for that, I can just demonstrate to you. If I just, we'll just add a few of these monitor commands. And if we do add R1, R1, R0, if I just do this here. Well, you can see, even though we're doing an add command, every time we add this value, the number in R1 is going down. And the reason for that is that we're effectively overflowing the register and ending up one lower than where we started because of this value. And that's why, as I say, there's almost no such thing as signed numbers within the processor. It's only the commands we use for comparisons that define the number as positive or negative. And the problem with this is, if we just take our example code from here and we compare, if we're comparing here -1 to 20, then of course -1 is lower than 20. But if I take this and I put this value in my unsigned version here, and if we just enable that here, well, we've compared -1 to 20 here, and then we've branched, and now -1 is obviously lower than 20, but we've used the wrong branch commands here, and we've used the unsigned ones. And although this is -1 if we treat it as signed, it's actually about 4 billion or something crazy if we treat it as an unsigned number. And that's why things have gone wrong here, and that's why we've shown the greater than when actually R0 is less than. So we do need to be very careful to make sure we're using the right commands when it comes to our signed numbers, because otherwise we will get the wrong answer. So we just need to make sure we understand things there. So as I say there, the signed numbers are effectively very, very high numbers, and the way things end up working is that half of the range of a register become negative, just slightly over half, and half become positive. And the length of our register doesn't actually matter. So if you think of an 8-bit register, just for simplicity, an 8-bit register that's signed can go from -128 to +127. And if you think about 128 in hexadecimal, that is a register where there's a bit 1 followed by 7 zeros. And the effect is that a negative number in assembly will always start with the first bit as a 1. And we can use this to check if a number is signed, and what it effectively is doing, the processor, is it's setting the negative flag if the top bit of the register's value is 1. And we can just show that just here if we run this sign example here. So we've loaded in a value of -100, which is apparently hexadecimal 9C. I couldn't remember that. We will have to kind of take its word for it here. But we could just test here if we go to decimal and we do -100. And then we go to hex, or we can actually just see it there. Yeah, there we go. So we can confirm it's correct, but as I say, I can't remember the negative hexadecimal numbers or anything. But as I say, that's apparently what it is. So we've loaded that in, and we've basically done a jump to either show a plus or minus. So we've got two options: BPL for branch if plus, and BNI, which is jump if branch if negative. And we have in this case branched if negative and showing the minus. But if we change our value to be a positive number, I'll just enable this version. Well, now you can see we've shown a plus, and you can see, of course, the top bit is 0 now, and there is no N flag set here. And that's a very easy way we can test the sign of a number. Of course, we could also compare to 0, but this is going to be faster. So if we need to check the sign of a register or a value, we can do that with that sign flag, the negative flag, and those commands BPL and BNI. Now another one relating to signs is the overflow. Let's have a look at the overflow. So what is the overflow? Well, the overflow is when we've accidentally converted a number from a positive or a negative. As I say, if you think of 8-bit, plus 127 is the highest that a positive number can go, and minus 128 is the lowest that a negative number can go, but minus 128 is actually plus 128 in unsigned numbers. And so if we subtract minus 1 from minus 128, we would end up with plus 127. Maybe that sounds a little bit crazy. I apologize if it does. But as I say, the thing we've got to deal with is that if we accidentally overflow a negative number, or a positive number, we will flip into the opposite sign. And if you were doing your mathematics, and if you think of your bank balance, and if your bank balance was in the red and it was very, very low, if you kept subtracting, eventually you would go below the limit of the register and end up with a very high positive number, which would be a serious problem. Just an example, of course, you wouldn't use those kind of numbers in accounting, but as I say, it's just a funny example to show why it's important to make sure that you're not accidentally changing the sign of your registers because of the limits of the numbers. So here we're loading 7 and a load of F's here, which is the absolute limit of a positive number within signed mathematics. We're then going to add just 1 to that, which is going to convert it to 8 and then a load of zeros. And if you think about the top bit is 0 here, so this is a positive number, but when we add that 1, it's going to become a negative number. Let's just see what actually happens here. So we have added 1 to our negative number here, and this has converted to 8 and a load of zeros, and that has set the negative flag, and that has also set the V flag, which is overflow, and we've shown a V here. BVS means branch if overflow set, BVC means branch if overflow clear. Okay, so we've unfortunately caused an overflow there. Well, if we made a slightly smaller positive number when we added 1 here, well, we're still within the limits of the positive number. The negative isn't set, so we've got no overflow NV. That's what I've used there. And you can see that is okay. Now, this, of course, could happen in this opposite direction as well. If I just load this in here, and if I change this here to 80000, and then I do subs 1, and I run again, well, in this case, we did have a very large negative number here. We subtracted 1, we've gone over the limit of the negative number, and now we've got a positive number. You can see the N flag has gone, and we've shown the overflow again. So we do have to be very careful if we're dealing with negative and positive numbers that we're not going to overflow the limits of our values here. So that's what the overflow is for. That's what it means. And that's how we can test for it with BVS for branch if overflow set and BVC for branch if overflow clear. Okay, so that's how we can work with our overflow. We do have one slightly comedic option here. I have no idea why you would want to use this, but for completeness, we have a BNV, which means branch never, it will never occur, and BAL, which is branch always, which will always occur. Good luck with those. I don't know why you would want those. I mean, branch always is just the same as your regular branch, but branch never will never occur. Let's just prove that for some reason. I'm not sure why we have, but we've shown a J because we did the jump here, and I don't even remember what no jump would have shown. Oh, it shows a full stop. Okay, so there we go. As I say, they're there. Enjoy them. I think the only time I could think you might want to use these is if you were, and I'm not suggesting you do, you were using self-modifying code, which is where the code reprograms parts of its own hexadecimal source code. This is a big thing in Z80 and 8-bit processing because you need the speed. But on a processor like the ARM, I think the speed is not going to be required so much. And also, I think you're going to have a lot more difficulty because the commands are so big and the structure of them is more complicated. But I could imagine that you could maybe convert a branch if carry set to a branch never if you wanted to disable it, or equally a branch if 0 or something to a branch always if the code's requirements had changed. But as I say, I'm not suggesting you ever need them. For completeness, as a tutorial on condition codes and branches, I wanted to mention them, but I think they're not something you're ever going to need. Now, we've been doing all of these based on branches, so all of these conditions. But as I say, the ARM actually isn't limited to that in any way. We can actually use these condition codes on the vast majority of our commands. And so in the same way, we've been doing branches to show characters based on conditions, but that's just a simplification for this tutorial. We can actually do that in a much simpler way. So in this example, we're going to show a less than or a greater than based on a comparison of two values. We're going to compare 10 to minus 20 in this first case. We're setting the flags just here. And then we're going to load an equals into our 0. And then we're going to, but if the flags say that the value was less than, when we did this comparison, remember the S was here, so the flags were set. So this didn't affect the flags because there's no S. And then this will check if the flags imply that the value is less than, the flags set here, and we'll load the ASCII equivalent of a less than symbol into our 0 here. Again, this doesn't change the flags. So this time we will check if the flags say that the comparison was greater than, and we will load a greater than symbol in here. So we've got three commands here which will either result in the R0 containing an equals, a less than or greater than, based on the flags of the earlier command just here. Let's execute this. Okay, so in the first case we've got a 10 and a minus 20, and 10 is of course greater than minus 20, so we've shown a greater than. Now if we do the equivalent here and we just change this to 10, well, this time these two commands didn't do anything because the less than and greater than conditions weren't the case. So this move command was the only one of these three that executed, so we're shown an equals. But if we enable this one just here, well, you can see now we've got our less than. Now, of course, these all do rely on the flags still being set. If I, for some reason, put the S here, this command will now set the flags. So we would think that this compare would show that these two values are equals, but we've accidentally set the flags based on this movement here. So now the actual value is greater than. So we do have to be a bit careful with our work here, and we can only do this trick for short distances. But normally speaking, in something like Z80, we'd have to do jumps to jump over the commands that we're setting the value in R0 that we didn't want to occur. But with ARM, we can just say, well, this command alone only executed if this condition set. So we can do this. We can use this as a way of having a few commands that only occur in certain circumstances without a branch, and it makes our code cleaner. It makes the processor more able to predict what commands are coming next, which aids the speed, and it's really quite powerful. So I think it's the big advantage of the ARM compared to the other processors I'm aware of. There may well be other systems that use this, but of the ones I'm currently experienced with, this is really a shining function of the ARM that is really impressive. And as I say, considering the ARM2 had this in the 80s, I think it was, this was an incredible feature. And that's really one of the things that gives the ARM its formidable power. So there we go. Now, we've been over a wide range of commands there. I know they're a little bit tricky. Some of them you probably want to try out yourself, and you probably need to sort of remember them and things. Now, of course, some of the ones like the greater than and the less than, they use multiple flags, and fortunately we don't really need to worry about which flags are being set in a lot of cases. Now, some of the commands support these condition codes, and others, some of the more advanced commands, don't necessarily. What I'd suggest you do is, if you go to my website, there's a cheat sheet you can download, and that will show a CC where this condition code option is there, and that is the commands like the ones we just saw, the move command we just tried out, where we can put the condition codes at the end and have that command only execute if the conditions are met by the flags. Anyway though, I hope you found this interesting. I hope you've enjoyed it. As I say, go to my website, you can download today's source code and try it out, make a few changes and see how the how the flags change the execution of the commands and which jumps occur or which other commands occur, because as I say, it's not just jumps on the ARM processor. But whatever you do that, I hope you'll enjoy programming the ARM and programming in general. Thanks for watching today, and goodbye.